Thank you. I'm honored to be here on my first trip to China, and I congratulate the organizers on a very successful conference. I'll be speaking about work with some exceptional young collaborators, Johannes Knaut, Sarthak Tariq, who is here, Andreas Semberg, and Tremek Vitacic. P-adic numbers are a completion of the rationals with respect to a funny norm. Equation 1 shows that norm. It's funny because you would think that on the right-hand side you would have at least the prime number p to the power of positive v. But it's not that way. P is a small number in the p-adic norm, and that's what makes everything work. So for instance, the p-adic norm of p itself is 1 over p. The p-adic norm, pardon me, there should have been a subscript p right there. The p-adic norm of p squared is 1 over p squared, and so forth. Whereas, if you have some number, let's just say a, which is 1, 2, 3, up to p minus 1, its p-adic norm is 1. And by fiat, we simply say that 0 has p-adic norm of 0. Well, any general non-zero p-adic number can be written as a formal series of this form. Again, it looks funny because I'm running the series to arbitrarily large positive powers of p, but that's okay in a p-adic sense because positive powers of p become p-adically small. So this sum converges provided the so-called digits, a sub n, are bounded. And in fact, we can choose them all to be either 0 or 1, 2, 3, up to p minus 1. Let's get a little more intuition for this kind of expansion by working out the p-adic expression for the number minus 1 in the case where the prime p equals 2. First, we write minus 1 as 1 divided by 1 minus 2. That was trivial algebra. And then we expand this second expression as a geometric series, which is okay in the 2-adic numbers, because remember, 2 is small. So minus 1, when you write it, minus 1, when you write it as a p-adic expansion, a 2-adic expansion, expands forever to the left, and every digit is 1. Let me draw that. Let me draw this p-adic expansion in a way that will be, I hope, very suggestive of AdS CFT. I want to have a tree whose main trunk, if you like, starts at infinity and goes all the way up to 0. And I want to consider paths on this tree which start at infinity and go upward, as I'd like to think of it, upward toward the boundary of the tree in some particular way. And the way in which I steer up through the tree will uniquely determine a p-adic number because it amounts to specifying the expansion that I wrote in the previous page. The information in that expansion is encoded in the path in the following way. Where you leave the main trunk determines the overall p-adic norm. So to back up for a moment, the overall p-adic norm is determined by this overall factor. So that first factor is controlled by where you leave the dark red trunk. And then every subsequent choice you make in steering your way up the tree corresponds to choosing the next p-adic digit from right to left. We should think of each node on the tree as a rational approximation to the eventual p-adic number that we find. The p-adic number that I found in this particular path ends in the digits 0010.1, and a rational approximation of it is this number a in the tree, whose p-adic expression is 0.1. An important property we'll have to keep in mind in future slides is that the p-adic numbers have a subset of the p-adic integers that is numbers with no fractional part, no 0.1 or 0.11. So p-adic integers are in fact a compact set. They're the numbers whose p-adic norm is no greater than 1. Another important set for us will be the p-adic numbers whose norm is exactly 1. In other words, the unit circle in the p-adics. And that is this set U sub p. All right, so of course, you can see where I'm going. I want the tree to be p-adic AdS, or something like it. And I'm going to introduce a depth coordinate, z0, valued in integer powers of the prime p, whereas the boundary coordinate z is valued in the p-adics. And then the depth coordinate of p-adic AdS, the z0 coordinate, should be understood as a sort of p-adic accuracy. The approximation we were talking about, the approximation a to z, is good to within an accuracy that is the p-adic norm of z0. Now, the rest of my talk is going to be organized as follows. I will describe some previous work, including the p-adic string, eternal symmetry, and p-adic field theory. I will tell you another wonderful fact, although I won't prove it, about this tree, which makes it really seem like AdS. The tree is in fact a quotient of p-adic relatives of SL2R and its maximal compact subgroup. I'll tell you also about field extensions of the p-adics that lead to trees that are analogous, I claim, to Euclidean AdS n+1 for any n. And then I'll tell you about a natural classical dynamics on the tree that allows you to define correlators in a p-adic field theory. It's very similar to the story of bottom-up AdS CFT. In particular, I'll show you, well, not 2-point functions really, but I'll show you 3-point and 4-point functions, which exhibit interesting comparisons to the usual formulas for real AdS n+1. But there's a crucial property of the p-adics that I'll come to only late in my talk, called ultrametricity, which makes the 4-point function much simpler than you expect. I will also describe at least a little bit of another work that came out only shortly after ours by a Caltech group, and in particular they described the p-adic analog of the BTZ black hole in Euclidean signature. And I'll indicate a few possible future directions. The p-adic string is well known, so let me go through it quickly. It's based on the analogy between the two lines of equation 5. The symmetrized Venetiano amplitude, which John Schwartz told us about, can be expressed in terms of what's called a local gamma function, which is a small modification of the usual Euler gamma function. And when you write the Venetiano amplitude, the ordinary Venetiano amplitude in this way, it generalizes very simply to the p-adic numbers, where now these local gamma functions have a closed form expression, and I wrote it down for you. The only thing I haven't told you, really, is how to do p-adic integration. But it's really quite simple. Essentially, all you have to say is that the measure of the p-adic integers is 1, and the measure of some p-adic multiple of any set is going to be the p-adic norm of that multiple times the measure of the original set. An amazing fact is that the product of all the local gamma functions equals 1. And this leads to a so-called AdElic relation, first written down by Freund and Witten in 1987. For the Venetiano amplitude, you write the Venetiano amplitude as 1 divided by a product of p-adic amplitudes. This amazing formula may seem a little less surprising if you check that for a rational number z, the ordinary absolute value of the rational number, which I denote as absolute value with subscript infinity, is similarly 1 divided by the product of the p-adic absolute values. Now, what I'm after in p-adic AdS CFT is correlators, very much of the sort that entered into the Venetiano amplitude. Remember that up to issues of gauge fixing, we could write that Venetiana amplitude that I had in the previous transparency as some correlator of composite operators written in terms of a free scalar x. So let me just try to study a little bit more systematically this kind of correlator in a p-adic context. And of course I expect that there will be 2-point functions of a form like I've given here, and 3-point functions of a form that I've given here. And this functional dependence on the positions z, all of which are p-adic numbers, will be completely fixed by invariance under p-adic linear fractional transformations, which play the role of the conformal group. Of course, when we get to 4-point functions, we don't expect such a simple dependence on the z's as I've written in equation 9, because there are cross ratios, and I'll have more to say about them soon. Now let me come out with the amazing assertion that's been known since 1972, that if you take the maximal compact subgroup of this p-adic conformal group, that maximal compact subset happens to be PGL2 of the p-adic integers. And then this quotient really is the tree previously discussed. I'm not going to demonstrate it, but we can talk about it afterwards if you want to know how that happens. Now, having established the hope that this tree is the right p-adic replacement for AdS, I want to do some kind of AdS CFT on the tree, starting from the bulk and deriving boundary correlators. So here we go. If I were doing it in ordinary Euclidean AdS2 for the reals, I would write down some action for a scalar of such a form, and I would turn the crank of AdS CFT. Well, let me just write down an action for a scalar defined on the tree. Phi sub A is a real number defined at every node A of the tree. And so I write down some action which is also a real number, and I'll turn the same crank of AdS CFT and derive the kinds of correlators that I wrote down in the previous transparency. And I'll do it step by step, very much in the way that we would have always done it for the real case. In particular, step 1 is to find solutions to the linearized equation of motion for this scalar phi. And in particular, to find a bulk-to-bulk propagator which takes this form, where I'll tell you in a moment what this zeta sub p thing is. D of A and B is the distance on the graph, the distance on the tree, meaning how many steps do you have to take to get from A to B. It's a well-defined number because the graph is a tree. And there's a relation between the mass, again, a real number, and the dimension, also a real number, which is quite reminiscent of the usual AdS CFT relation between bulk masses and boundary dimensions. Now let me tell you about the so-called local zeta functions. We define a local zeta function for the reals in a way that seems rather arbitrary, but let me just say that's my definition. And then I have some perhaps more motivated definition of a local zeta function for the prime p. It's motivated because I can write the Riemann zeta function as what I think is called an Euler product over all primes p of these local zeta functions for each p. If you add in a relation for gamma functions, then this previous claim that the product over all v of the gammas equals 1 is an equivalent statement of Riemann's functional relation to the zeta function. My other little technical detour here is that I really want to tell you about AdS n+1 / CFT n. And to do that, I had better introduce n-dimensional vector spaces over the p-adics. Well, there's a nice way to do that. It's the so-called unramified extension of p-adics, whose degree n is to be thought of as the dimension of the vector space that we're considering over the p-adics. So I've tried to draw it as well as I can for the case n equals 2. This would be called quadratic extension of the p-adics. And there's a norm there's a norm that I'll call norm subscript Q that is very similar to the p-adic norm, and they're the same depth of direction z naught is still useful. So there's very little difference really between the two cases of unextended and extended p-adics. Now, let me speed up a little bit and remind you of the way we compute 3-point functions in the real case. I simply take bulk to boundary propagators, I make them meet at some bulk point, I then integrate over this bulk point. The bulk to boundary propagators, it turns out, are nicely expressed in terms of the local zeta function. I'll have more to say about that in the future. And the 3-point function comes out as the obvious product of the z, ij's, up to a normalization, which itself is easily written in terms of the local zeta functions. I like this expression for this coefficient C000 because it doesn't involve the transcendental number pi. Pardon me. It doesn't involve pi, and in fact, if we simply replace infinity by p, we wind up with the correct answer for the 3-point function of a p-adic field theory, according to the prescription that I'll develop in the next transparency. So in other words, we can continue from the real case to the p-adic case as soon as we've written everything in terms of local zeta functions in a surprisingly easy way, except for one little detail. Here, you see there's a factor of 2 in the denominator, and here there's not. That's a bit of an embarrassment to us. We did not give any deep explanation for that mismatch. All right, so here's how you actually do a calculation in p-adic CFT. You figure out what the bulk to boundary propagator is. I wrote its form. Perhaps we need not discuss it in detail. The coefficient is determined in the usual way. And then, in order to calculate the sum over all positions x, it's convenient to consider the bulk to boundary propagators as running all to the point C, and then use bulk to bulk propagators to run from C to X. And so you wind up with a sum of this form that controls the overall normalization and gives you this claimed answer that is so similar to the real case. Now let's go right on to the 4-point function, which is very entertaining because you can write it all in one line for the real case and the p-adic case, as long as we're only looking at the leading logarithmic behavior of the 4-point function in the real case. By leading logarithmic behavior, I mean that if we take z12 and z34 small compared to z13 and z24, then the complicated 4-point function in the real AdS CFT situation has only this simple logarithmic behavior in a limit I just wrote. And that same behavior is recovered for the p-adics using a calculation very much similar to the one I just showed you in the previous transparency. It's so similar that, as you see, I didn't even write subscript infinity or subscript p. You can write either one as you please, and the formulas are right. Now, what's more remarkable, perhaps, than that continuation from the reals to the p-adics is that the full expression for the p-adics, the full 4-point function, at least the full 4-point function that comes from a contact diagram, is very simple. This logarithmic behavior that I wrote in equation 23 is here, and it's corrected only by a couple of small finite terms inside square brackets. I'd like to ask, where did this logarithmic behavior come from in the sense of p-adic numbers in the tree? And why is there no dependence on the other cross ratio that I wrote in equation 24 as u tilde? More often it would be called v, but I was using v for something else. Now let me tell you about ultrametricity. P-adic norms are ultrametric in the sense that the p-adic norm of x plus y is less than or equal to the supremum of the norms of x and y. This seemingly innocent inequality implies a small theorem, whose proof I have all in this transparency. It says that if the cross ratio U is less than 1, then the other cross ratio U tilde equals 1. How can it be that from only inequalities we recover this equality? Well, the key is the so-called tall isosceles lemma. Suppose you have x plus y plus z equals 0, then up to relabeling of x, y, and z, you'll have x equals y greater than or equal to z, where I meant to say really normal of x equals normal of y greater than or equal to normal of z. The proof of it is instructive. We can get this bit for free just by choosing of x, y, and z the one with the smallest norm. So having done so, we only have to show that the two of larger norms have equal norms. And to do it, we use the ultrametric property twice. The norm of x equals the norm of y plus z, and that must be less than or equal to the norm of y, because we assume that the norm of z is less than or equal to the norm of y. Likewise, we can show that the norm of y is less than or equal to the norm of x, and that's what we want. Let me not go through the proof of this theorem about cross ratios, but just assure you that it is a repetitive application of this tall isosceles lemma. I'm running out of time, but I can tell you where the log u came from. If u is less than 1, then there's a diagram similar to what I drew here, where z1 and z2 are essentially close together, and so are z3 and z4. And when you connect them on the tree, that is to say, when you connect them in the bulk, lines on the tree, paths on the tree from z1 to z3 and from z2 to z4 run together. They coincide for many steps. The number of steps along which they coincide equals minus the log of u. And now you can see why there's a log in the 4-point function. This subway diagram, as we like to call it, since it looks like the diagram of a subway system, allows us to shift x all over the P-adic tree. And as we shift it as far as it will go along this central leg, there are log u equivalent locations for b. And that's where this log u comes from. Okay, the log also suggests some kind of anomalous dimensions in the dual field theory. For lack of time, let me just speed through it and suggest that there is an operator O squared whose dimension is slightly different from the dimension of O. And then if you use an OPE to develop this 4-point function of O, you would naturally expect that you get an expression like this second to last one, which when expanded in small delta does give you the desired logarithm. And a similar mechanism, as has been previously mentioned in this conference, is responsible for log u behavior in classic AdS CFT. Let me tell you just one important thing about P-adic field theory, and that is that they look terribly like ordinary field theory, but simpler. There's a Fourier transform. There can be propagators. This exponent s need not be 2, that's a funny feature, but it's not essential. There are loop divergences, which you might regulate in the ordinary way. There are, it's believed, Wilson-Fisher fixed points. But there's something very special. The something very special is that when you do Wilsonian RG and you integrate out a momentum shell, the effective action has a very simple form. The effective action has this kinetic term for phi, which does not get renormalized. And then it has some effective polynomial action for phi itself. So why, in integrating out the hard momenta, do we not renormalize this or generate some other sort of derivative interactions? Well, it's because of ultrametricity again. I illustrated it perhaps in too much detail by computing this underground diagram, which in ordinary 5/4 theory would renormalize the kinetic term. But because of ultrametricity, it does not in the P-adics. And I believe that this phenomenon of not generating derivative terms is going to be related to the simplicity of the 4-point function. I believe that the OPE of O with O is probably very sparse effectively with no descendants. I think I'm out of time, so I'm sorry I couldn't mention some other work by the Caltech group and the important background work by the Stanford group, but I'll leave them in my transparencies for people to read. And let me just go straight to conclusions to tell you that holographic direction is very natural in describing the P-adic numbers. This depth coordinate Z is P-adic accuracy. If you follow your nose in formulating simple classical dynamics on the tree, you get endpoint functions closely analogous to standard results in AdS CFT, but written in terms of these lovely local zeta functions. I'd like to ask, why are the P-adic results so close to classic AdS CFT, but not quite the same? I'd like to ask, what about fluctuating geometry in the tree graph? I'd like to ask, what about Lorentzian signature? I don't have good answers to any of these questions. Ultrametricity leads to these wonderful simplifications, especially in the 4-point function. But one more area where I think there's opportunity is to give a more symmetry-based presentation of P-adic CFTs, and perhaps even ambitiously define explicit AdS CFT dual pairs. Thank you.
I have two questions. In the usual AdS CFT case, the coordinate Z0 is usually associated with some kind of normalization group scale. Is it the same here?
Absolutely. There's a well-known story from P-adic field theory, especially Lerner and Misrov, starting from the so-called Dyson hierarchical models, where you do explicit step-by-step spin blocking from one layer of the tree to the next. And that spin blocking leads to even some rigorous results by Tsinghua on a normalization group.
And the second is ultrametricity is the property of states in spin classes. Is there some connection to this order?
I'm sorry, I don't understand the question.
Ultrametricity is the property, according to several people in the past Parisian company, of the state space of spin classes. Do you think there will be some connection to this order?
Well, probably yes, but I can't offer you any wisdom.
Okay, so just two comments. So one is that in the symmetry version of the model, you can actually work out the OPE in detail and indeed confirm that there aren't any descendants. You can see, for example, that it obeys associativity even without descendants. I guess we tried to interpret it in terms of the sort of, that the P-adics are sort of more discrete than the real numbers, so the derivatives aren't really necessary to give you a solution of crossing. The other comment in response to Elias's question was that, if you want to view this as de Sitter space instead of anti-de Sitter space, which is how we were viewing it, then Deneff and Aninos and collaborators have for a long time been saying that this sort of ultrametricity should be related to sort of classic behavior in de Sitter space. I'm not sure if Frederick is in the room right now, but I want to say there is quite a bit of literature.
Thank you.
More questions? Or no questions? Let's. There is. Okay. I couldn't see it. It's right in my eye.
No, that's okay. Thanks. No, I just wanted to sort of follow up on that, but actually ask you. You had a transparency you skipped over on eternal inflation, and could you just tell us a little bit about that?
I'm only giving a partial summary of the work by Harlow and collaborators. He's right behind you, so I'm sure tell you more. It's an idealization of internal inflation in which a given causal region can nucleate new de Sitter vacua that fall out of contact with one another and then split again. And you might think of the future boundary as the P-adic numbers, which because of their disconnectedness, as Dan points out, might be more descriptive of a late time multiverse than the ordinary forward time boundary of de Sitter.
Any more? No? There are no more questions? Okay.